is Jasmin Raissy from University of Bordeaux, and she's actually got a title on the board. So I think exactly right there. It's a very complex
Thank you very much. Well, as it's usual, I'd like to thank, well, the other organizers, because it's weird to thank themselves, like really weird day. So, well, as a statement, like, please ask as many questions as you feel like. I mean, the point is all this is that you get out of here with a hint of what has been done and why do we care about studying an invariant Fatou component for polynomial skew products in C2. And second, well, actually, for several reasons, well, Tom's talk came first, which is kind of a little weird. It would have been better to have this first, but it's okay. I mean, it's how life goes. So you already know some results and some of the techniques that we've been using, but today we are going to get a step back, and I'm going to try to explain to you why do we care about invariant Fatou components and why especially polynomial skew products in C2. So before going to C2, I think it's, even if we all know it, it's always reassuring to state on the board things that we all know, right? And so what do we know in dimension 1, okay? In dimension 1, and you'll see that this is where my motivation comes from. And actually, I have to thank Phil, because he already gave a very nice introduction to wandering domains. But, well, okay. Okay, let me start from the very beginning. So in dimension 1, we are going to be, before talking about transcendental entire functions, we're going to talk about rational functions, okay? So if I take a rational map of degree d at least 2, we introduce the Fatou set as the normality set. For the family of iterates. And the Julia set as the complementary of the Fatou set. And of course, actually, the Julia set is where the chaotic behavior is going to happen. But, and we always say, I mean, I've heard many people say, well, maybe I can, well, I'll re-raise it later. Many people say, okay, we know everything we want to know about the Fatou set, and so it's a boring set. Well, okay, yeah, it's maybe the boring set, but, well, so the Fatou set is not connected. Well, for rational maps, it's like, it's kind of boring, right? So the Fatou set is not connected, so you can have, well, in general, the two components, which is a connected component of the Fatou set. And I'm not going to put on the board my favorite example, which is d squared, because we all know that. But I'm going to put on the board Fatou's classification of invariant Fatou components and Sullivan's result. So actually, I like to give it to Fatou because Fatou conjecture it. And of course, as you all know, this is a contribution of many people. So Fatou proved some of it, and then, well, it was completed. So you take f rational degree at least 2. You take omega, an invariant Fatou component. Then omega is one of the following. Sorry, I'm short. I will try to make my best. So it is either a super attracting, well, or attracting Bayesian, meaning that you're going to have a fixed point inside omega, and every orbit is going to be smashed on this fixed point, and the derivative at the fixed point is going to be less than 1, or you're going to have a parabolic basing meaning that, well, this time the fixed point is on the boundary of the domain omega, and everybody is going to converge to this fixed point in some very good way. And the derivative, you can prove that in this case is 1, or you're going to have a rotation domain. Rotation domain. So, which could be simply connected. The Siegel disk. Well, we've been hearing about Siegel disks yesterday, so maybe I don't need to remind what a Siegel disk is, okay? Or it could be doubly connected, and it could be a Hermann ring. And I never know how many N Hermann has, whatever. All right. And actually for today, so if I add here polynomial, I have seen color choke. So if I just care about polynomial, so if f is a polynomial, then Hermann rings are not there. Okay? All right. And then you have Sullivan's result. Telling to you that, well, if you have a rational function of degree d at least 2, then for 2 components are free-periodic. Meaning that, well, they will go back to themselves or to an image. Okay, so, and then usually when I give a talk about for 2 components, I say, this means that we know everything we want to know in dimension 1 because, well, if you have a pre-periodic for 2 component, well, up to an iterate, you're going to be one of these. All right? So now you go to higher dimension. So I hope we are all good so far. Okay, I see people yawning, so it's boring enough. Good. So now let me go to higher dimension. So I'm going to do what my students don't like me to do. I'm going to erase and then, okay. So, well, first of all, what you have to ask yourself is which kind of map am I going to talk about? All right, so higher dimension for me will be today dimension 2, which is more than enough. And then, well, okay, you could work in C2. You could work in C2 hat, C2 hat. Thank you. Or you could work in P2 of C. Which one would you like to take today? Actually, if you really want to mimic or to try and understand what happens from that picture, it's like, is it going to be the same? You should choose a compact space. So forget about C2. And you should choose one which is a complex manifold. So forget about this one. Okay? So, of course, you could also choose C2 and consider polynomial automorphisms of C2. I mean, there are many choices that you can do, but for today, let's choose P2 of C. So, sorry, I'm a kind of a psycho-rigid person. And so whenever I'm in higher dimension, everything becomes capital for some reason that I don't understand still. So if I take P2 and I take a holomorphic map from P2 to P2, and don't worry in a minute. So if you work in P2, if you know what P2, well, what working in P2 means, that it's perfect. And if you do not, I will try to keep it simple for you. So I will make it simple in a moment. So you take a holomorphic map. And why do you really care about being in a compact space? Because, well, normality set makes sense. So you will still be able to talk about the naive, if you want, Fatou set. And the Julia set is going to be simply, well, same definition. The complementary set. So it's going to be the normality set, but oops, we will not have Montel's theorem anymore. Okay, that's life. That's why I have a job, I think, so it's fine. I'm happy about that. All right, so, okay, what is the easiest way to go in higher dimension? To try and guess what happens in higher dimension. Direct products. So if you want to understand something, if you want to say something meaningful, maybe this is not the best idea, but at least you can always say to people, everything that I've seen in dimension 1 will still work in dimension 2 because I can consider direct products. So you can consider a map. POW. And now you tell me, if you're awake, that this is not P2, right? So why am I writing it like this? Because in here, I might choose to see P2 as C2 plus the line at infinity. And so I could tell you, okay, I'm going to take something which is, well, F and G are homogeneous polynomials. Sorry, not homogeneous, polynomials. I'm already ahead of it, of same degree. At least 2. And this means that I'm considering what is called a regular polynomial map in C2. It's regular because I can extend to P2 of C easily. What do? Well, I will consider, so if I consider in P2, sorry, I know this is not exactly standard, but that's how I think about it. So I can consider the map F tilde from P2 to P2 of the form T is simply going to be, so let me see if I do it right. I think I'm not mistaken. Okay. Yeah, thank you. I was not sure about. So
we didn't have to write that in there because that is very much in common.
Good. So this is going to be a holomorphic map from P2 to P2, okay, of degree T, D, and well, you see that there is no indeterminacy set because the only point where these three objects are 0 is going to be 0, 0, 0, which is not in P2, so everything is fine. We're happy. And so this is going to be my holomorphic map. So, and if you think about it 2 seconds, well, actually, it's also easy to understand what happens on the line at infinity. Okay, so exercise. If you ever, so I don't know why, but I hear myself double. Maybe it's just, anyways, sorry. It's maybe myself, I'm getting old. So if you ever get bored during the talk, I'm going to leave you exercises. So exercise 1, well, try and guess what happens on the line at infinity for this map if you take 2 degree D polynomials. All right, so if you consider this, then what happens to the Fatou set? Well, what makes more sense, if you are considering really direct products, you might want to say, okay, this is a one variable one, this is a one variable one, it's a polynomial, I can extend it to P1, okay, and so actually a direct product gives you more of a map in P1 cross P1. And why do I talk about this? Because in here, if I consider the Fatou set defined with respect to P1 cross P1, Well, the Fatou set of capital S is going to be the Fatou set of little f times the Fatou set of little g. So you don't lose anything, you don't gain much, but it's reassuring. Okay? And actually, if you consider normality in P2, well, the Fatou set of f will contain more or less this guy. The only problem that you have is when you go to infinity. Okay? So if I'm going to write it like this, when I intersect it with C2, this is going to be the Fatou set of f. That I wrote it down because I am always doing it wrong. I didn't write it down. Fine. Okay, anyways, I'll write something more or less. It's more or less this. So if you forget about going to infinity, that's, you can still think that you're going to have products of Fatou components. All right? So now, it is natural to ask, okay, I was taking very, very particular maps. I have no idea what the time is. I'll see it later. All right.
We are trying to say that compactification does not affect on
Sorry?
the compactification has no effect on the bounded.
Yes,
on the,
that's what I'm saying. Whenever you say bounded, the compactification has no effect. And actually, well, since we already had Tom's talk, if you remember, well, we were talking in his talk, you were going to infinity. Well, still it doesn't really matter. So actually what it really matters for the normality compactification, this is just a parenthesis for the experts, is really if you're going to infinity or not. And so if, well, essentially you just can consider the C2 hat. And sorry, I assume that everybody was familiar with that, but C2 hat is just a one-point compactification, usually called the Alexandrov compactification of C2, which is not a complex manifold in dimension 2. All right, so thank you, Luca. Are there other questions while I erase? No? Okay, good. Or not, who knows? Maybe I lost you all already. All right, so now where am I? So what do I want to tell you about? Okay, good. So yes, I'm not following myself at all. Okay, good. So let's say we have question 0. Is that anything that can happen in higher dimension? So is that all? Is higher dimensional, well, dynamics richer than this? I mean, you can ask, I mean, what do we really care? And you know already, because you had Tom's talk, that it is. But is it only when I talk about transcendental objects, or is it really richer? Well, okay, so you can ask, okay, let me think for 1 second. I'm going to take a direct product, sorry, not a direct product anymore. I'm going to take a skew product. So in C2, this is going to be, so I'd like to be consistent with myself, yes. So f of dw is going to be, well, in one variable, I'm going to say one-dimensional, but in the other one, I'm going to be two-dimensional. Okay? So I'm not exactly working in C2, I'm working in C1.5, because on one side, I know exactly what happens, and I'm going to take, well, a polynomial skew product. Why? Because I want to study this question on P2. Why do I care? Why are we working on this? Because, well, Sullivan result, that was more or less here maybe, works in dimension 1 for polynomial and rational maps. We know that it doesn't work for transcendental entire functions. We also know that it doesn't work for transcendental entire biolomorphism in C2. That's, if I'm not mistaken, Fornes and Sibony. But what about the compact case? So there was this question, can we have a wandering domain for a polynomial endomorphism in C2, which is regular? So can we have a wandering domain in P2? And so the idea was, and that's not my idea, of course, so that the idea that was among the experts, like I would say Fornes and I would say Ljubich, was that, well, you cannot use direct products. So what about using skew products, which is something that you can control somehow? Because you have this one-dimensional part. And, well, instead of starting with transcendental time function, which is kind of a little more difficult, let's try to start with polynomial skew products. So that, well, for this guy, and just to check what happens in the bounded Fatou part, okay? Whenever you don't go to infinity, what can we say? If you stay in the bounded part, well, you know exactly who the Fatou components for this guy are, okay? So you're going to have, and actually, oh, sorry, I erased it. But what you're going to have for G, you're going to have attracting mesons, parabolic mesons, or Siegel disks, okay? For invariant ones. But I mean, they're all pre-periodic. So up to an iterate, you can forget about periodicity. You just take the invariant ones. All right, you take the invariant ones. And what's really important in here is that you always have a fixed point. So let's say, okay, please let me write that my fixed point is 0. Because anyways, I can change coordinate, I can make it 0. So there is no point in having it like 100 over 42, okay, plus I. So if G of 0 is 0, well then f of Z0 is going to be, well, okay, let me do it for you. So what am I doing? I'm sending W equals 0 into itself. Okay, now this is the tricky moment. When you work in higher dimension, you cannot draw. So you draw and you ask your audience that, well, you know, C2 is going to be R2 for today. But now in a moment, I'm going to enlarge it because it's a complex plane. You shouldn't forget about that. And if you have a complex plane, so what happens to this map? Well, this map is going to, it's just a one-dimensional map, right? So I have f of Z0 that I'm going to call f0 of Z as if it was a one-parameter family. If W was a parameter, it's just that it's not varying autonomously. Whenever you change W, well, in here it's changing, okay, when you iterate. But if W is 0, then I have this one-dimensional space, and I'm going to have, again, a polynomial map on this guy. So again, if I consider the Fatou components of F0, I have all the right to do it, right? And so in here, well, the dynamics is one-dimensional. On W equals to 0. And so now I can ask, okay, I have my, so yeah, treat me, I change my mind, as Tom knows, every once in a while, but for today, this is W and this is Z, okay? So what happens in here is that, well, on this invariant line, I have F0, and I can ask to myself, say W equal to 0 isn't a Fatou component for G. Okay, say you are in an attracting domain. So what happens to my fibers, which are not invariant? So I have a fiber, and it's going to converge somehow to the invariant fiber. So if I could think about what was happening for direct product and it was still working on, well, if I have a Fatou component, do I have another color? Yes. Red. So if I have a Fatou component, say again it's invariant up to an iterate. In here on the invariant fiber, well, I can ask, is it coming from a two-dimensional one? That's the bulging that Tom was talking about, right? So I get to question 2. Sorry, question 1, because it was question 0. So let me write it as I wrote it in here. Are you still following me? Is it a good space? Do you want me to go faster? I can do faster. I can also do slower if you'd like to. So do all the two components, say omega f naught of f naught, bulge to two-dimensional, the two components for f. i.e., so what do we mean by bulging? Bulging is really, does it get a little inflated? Okay, I'm not saying, it's kind of a semi-local thing. I'm going to ask something about the whole Fatou component on the fiber, but I just want to know if in a tiny neighborhood of the invariant fiber, it's going to be two-dimensional. Do I have normality? So there exists omega f in the Fatou set of capital F, such that when I take omega f and I intersect it with w equals 0, it contains omega little f naught. And actually, you can even ask more, are they equal? If so, do we have equality? All right? And again, I left it up. It's fine. And again, what you can also ask is, okay, imagine this happens. Imagine all these little one-dimensional Fatou components are indeed bulging. Can I have what I didn't have in the direct product case? Can I have a wandering Fatou component coming nearby an invariant fiber? I'm going to put it here. So this is my question 2. Sorry about that. Is it possible to have a wandering Fatou component for f? Well, coming near the invariant fiber. Okay, so that was the motivation for studying, well, from what I understood, for studying polynomial skew products and bulging of Fatou components. So let me pause for 1 second. Are you still with me? Okay. Do you have questions so far? Yes.
So what is the relation between bulging and having a wandering array?
Very good question. Thanks for asking. This is the next step. So actually, so the idea is that, well, what I understood from what I've been told was that they were searching for these guys. And then you have to understand something about the Fatou set in higher dimension. The problem is that in other dimension, you don't have Montel's theorem. You cannot mimic what happens in Fatou's classification from dimension 1. So you have somehow to know what happens to the Fatou set, and you want to say, okay, I might come near this guy. So can I do it? And so actually, that leads to question 1. And well, so I'm going to write here on the board. So this is a case-by-case classification. So now you're going to study what happens in a superattracting invariant fiber. And then you're going to say, okay, what happens if I have this bulging of all these little Fatou components that are on the invariant fiber? Do I have enough space left for a wandering Fatou component? If it was existing, could it go nearby the invariant fiber?
Yeah, because it seems to me that existence of coaching is kind of the opposite thing
Exactly, exactly. The idea is,
to think about it.
yeah, so the idea is that, well, say you have all these bubbles. I mean, I'm sorry, I'm really bad in picturing this, but this is how I picture it in my mind. Welcome. So, and the idea is, okay, I have all these guys that are kind of bulging. But I also want to know whether there could be this wandering guy coming nearby. But if I come nearby, say a superattracting invariant fiber, isn't it that I'm going to be smashed eventually? Isn't it that I'm needing to be very, very small, so small that I cannot exist? And that's what Lilov proved. So thanks for asking, because it's a very good transition to now the historical part. So I know that I might present the story in something different, which is not the chronological order. I could give you the answer and that's it, the final answers. But I think it's also important that we do not forget how we get to somewhere. And so how do we get to a result? Well, by a collaboration of many little steps in the way. And so who's the first one? Actually, sorry, it's not the first one working on skew products. So does this answer enough? I mean, I'm waving my hands, but we are Italian, we understand each other. So okay, yes. Okay, just, yes, I forgot. Yeah, okay, I'm going to write it now. So because I think it's important to give credits, and also because we're going to see at least one of this person in this program. Where is it? Yes. So if I want to say something about the study of polynomial, well, dynamics, not in this way, of polynomial skew products. So I think the first one was Heinemann. Don't ask me what he proved because I don't remember. But I know that it has two ends. In 1998. And then it was continued by Johnson, who is going to come for 3 days, maybe 4. Anyways, at some point. At some point, we will see him. In 1999. And actually, the topology of Fatou components was studied by Roeder. And when was it? 2011. All right. And actually, before I can tell you, so, but this, trying to answer, so question 1 plus question 2 was initiated. As far as I know, I might be wrong, and I'm happy if somebody can correct me if I'm wrong, by Lilov. And I'm not sure, 2004 in his thesis. I don't think it's accessible because it was never published, but if you need it, I think I can find it for you. All right. So, but in order to be able to tell you what he proved, so I hope you agree with me that if I now take an invariant fiber, it's going to be a fixed point for G. And what are the fixed points that I'm interested in? Well, I'm interested in fixed points that are in the Fatou set or close to. So I'm going to give a definition. So W invariant fiber is, well, attracting F, well, modulus of G prime at 0 is less than 1, and it could be super attracting or simply attracting. Well, let's say geometrically attracting. All right? the difference in here, as we all know, is how fast you go towards 0. Or it could be neutral. Well, the derivatives have modulus 1. And it could be parabolic. F g prime of 0 is 1. Or elliptic. F, well, g prime 0 is 2 pi theta with theta irrational. But the only one that I want to consider are those who have a Siegel disk. Okay? So I should maybe call it Siegel, but we called it elliptic at some point, and so it's staying to be elliptic. I'm sorry about that. All right. And so what Leo proved, well, so in his thesis, he worked in the attracting case, both attracting and super attracting. So I will need to erase my questions, so keep them in mind, please. All right. So theorem for, by the way, since we were talking about mathopoli yesterday, I think he had a postdoc and then he decided that he didn't want to continue in math. I have no idea if he's happy or not, but he started something and his work was really important to this theory. So if I take, well, I'm going to stick to f from C2 to C2, polynomial. Well, actually, if I take a polynomial skew product, of degree d, meaning that the degree of f, which let me remind you is a two-variable polynomial, is equal to the degree of g, which is d at least 2, then it is automatically regular. Okay? Let me think. No, I'm going to add regular. Because we could have a drop in the degree in here, which I don't want. So the degree is a two-variable degree in here. And for the experts, what I don't want, if I take a regular, I don't want v to divide all coefficients, if I'm not mistaken. Or maybe it's the other way around, but anyways. Okay, now you don't follow me anymore. It's fine. So I'm going to take, all right. I'm going to take W equals to 0 super attracting for G. So I have a super attracting fiber. Then what you could prove is that, well, all Fatou components for F0 bulge. Second, there are no wandering domains. For F near W equals 0. And I left this little space because, so this is the statement as you find it in his thesis. So this statement is correct, but there is one little missing point in the proof. So if you say that all Fatou components for F0 are bulging, you are also considering the Fatou component at infinity. Okay, the basin at infinity. And he never proves, I checked it, he never proves that this is bulging, but it is. But he needs it in the proof. So you need it in the proof, and the proof is what I sketched a minute ago for Giulio. So the proof is really, I assume that I have a wandering domain and I'm coming nearby my invariant fiber. And what does he prove? He proves, so if, well, for 2, if there exists a wandering domain, let's say, let's call it omega tilde for f coming near w equal to 0, then it has to kind of be smaller and smaller, because it cannot touch the other invariant or pre-periodic Fatou components, and so it's coming near, and so you get estimates on its size. This is really an idea, huh? So you get estimates for its size, and eventually you get a contradiction. I'm not saying that it's easily seen from Lilov's computation, but this is what's happening. So the idea is that it's really is having these estimates, and these estimates are telling to you that the diameter of all the images is going to be smaller and smaller and smaller, because otherwise there is not enough space. And well, it gets to a computation, because then eventually you get smashed to the invariant fiber. But you couldn't get smashed, because once you touched the invariant fiber, then you were bulging for the component. You couldn't be wandering. So that's more or less the idea. Many computations. You don't want to see the computation today. So let me go forward. I'm sorry, I'm being slow. And what I was saying is that what he proves is that all orbitally bounded Fatou components bulge. This is what he proves. But it is true, and it's not difficult to prove, that actually the Bayesian at infinity for a regular skew product always bulge. So it's fine. But again, the devil is in the details, and so one should also take care of those. So voila. If, actually, let me put it, 0 is super attracting or geometrically attracting for G, then the Bayesian, so for a regular skew product, the Bayesian at infinity of F0 bulges. Not difficult, but one has to know it. And this is consistent with what Tom was telling to you on Tuesday, because in the example that we have, we exactly do not have a regular polynomial. We have a polynomial map of C2 from C2 to C2 that does not extend to a holomorphic map of P2. So it makes sense. All right, and it also makes sense with all the rest. All right. Oh yeah, and what I forgot to say is that for this one is a case by case proof. So you take an attracting domain, you prove it bulges. You take a parabolic Bayesian, you prove it bulges. You take a Siegel disk, you prove it bulges. And then actually you can even be good and forget about that you're working with polynomial, because essentially it's a local proof. You can also take a Hermann ring and you prove it bulges. So actually in here, in the super attracting case, all is none. And so, and you see I'm presenting to you in a very case-by-case basis. So we start with super attracting, now we go to the geometrically attracting fibers. And so, okay, if I want to tell you something about the rest, I will have to be a little faster. So for question 1, in the orbitally bounded case, the answer is due to Lilov in his thesis. So actually what I wrote in here, all orbitally bounded Fatou components for F0 bulge, it stays as it is. So in here, what it proves is that you have somehow, for those who know it, a strong stable manifold coming from every point. So in here, when you are your Fatou component on the invariant fiber, you have a strong stable. So it is really as if it was a direct product. So this is really strongly stable, but in here, at finite points, you have the same. So double arrow is strong. This is simply strong, stable manifold. The not strong, say stable manifold around all these points. So the proof is the same, more or less. It's like a linearization proof. So what about question 2? Question 2 was a different pair of hands because, well, if you're in the geometrically attracting case, the attraction is not strong enough. So what happened was, I'm going to be a little skippy. Sorry about that. So there were several results. So the first one, I think it's Peters and Vivas in 2016. Well, okay, by the way, all these dates makes no sense to me because these are publication dates. And of course, it took more time. So, but I didn't check yesterday the dates on the archive. I'm sorry about that. I think it can be another exercise if you get bored. Okay, so Peter and Vivas, so what they proved, the existence in a particular case of, let's call them wandering one-dimensional Fatou disks, which is not an answer to question 2, because it's just what I'm saying is that they could prove that in some example, this is W equals 0, and you could have something wandering around, but you have no idea if it's two-dimensional. Is it simply going to be a disk, a one-dimensional guy in a two-dimensional space, which is, okay, wandering around inside a Fatou component, which is invariant? And well, it turns out that it was the case. So what Peters and Smith proved in 2018 was that question 2 as, so question 2, I don't remember how I phrased it. Was it like, is there B, oh, it's up there, oh, thank you. Yeah, so the answer is no for, let me see, F0 sub-hyperbolic. And if, like me, you don't remember, this means there are no parabolic basins, no parabolic cycles for F naught plus all critical points. So you take the critical points of F naught, intersect the Julia set, are pre-periodic. If you don't read it, I'm sorry about that. So anyways, you had to add some condition on G0 to give an answer to question 2. Sorry, F0. And actually, in all the results that I can find on the all-knowing internet, it's always the case. So if you work in the attracting case, in geometrically attracting invariant fibers, either you have a condition on the rate of attraction or you have a condition of F0 that tells you that you cannot have wandering domains around coming nearby the invariant fiber. And I think it's still an open question whether you can have it in full generality, and I have no idea on how to take that. So, okay. So there is a theorem by G in 2020. Oh, I like this part. I might stay here. So if, I'm going again, I'm just going to tell you the rough idea. So if if 0 is sufficiently attracting for G. You can make it more precise. So you have a bound of the rate of the attraction. Then again, no wandering domains. So the answer to question 2 is no. All right. And the idea is, again, a good estimate on the size of Bulgarian Fatou components and forward orbits. All right. And I checked it yesterday. There was a new paper. Yes. So it's a new paper by G. I think there is also something in between that I forgot about. And Shen in 2026. So this year. Well, so no condition on G prime of 0, except that it's attracting and different from 0. But, so question 2, the answer is no, if F0 is unicritical. Okay, so I think I have 7 minutes left. Yeah, 8 to 7 minutes left to tell you something about the rest. So far, the attracting and super attracting invariant fiber have been the one most studied for question 1 and 2. What I should tell you, and you've seen that Tom has been working in the transcendental case for question 1. Well, actually, also question 2, because now we have the wandering bulging. So, anyways, all right. But question 2 doesn't really make any more sense for transcendental skew products. But there has been work for the parabolic invariant fibers. Well, I don't think you might find strange that we didn't exactly think about question 1 for parabolic fibers, because actually in the parabolic case, you will not have that the invariant fiber is in the Fatou set. So, because it's in the Julia set. I mean, the parabolic points are in the Julia set. So, for question 1, it's problematic. So you need to define bulging in this case. And we've not done it yet, also because parabolic dynamics has a lot of problems that I will not enter into, but I think you might see some in week 3 in 2 talks, if I check correctly. Xavier Buff is going to tell you something about what can happen, not for skew products, just what can happen. And I think Mathieu, if he doesn't change his talk, is going to tell you something about parabolic implosion in dimension 2. So, and Alexandra is here. And we heard a little about parabolic implosion in dimension 1 in Alexandra's talk. So, you know what you need to know for the moment. Okay, so, but what about question 2? Well, actually, question 2 is exactly related to parabolic implosion. Why? Because, I'm going to write on the board, then I maybe stop with that. I will tell you just one word about, So say you consider z plus z squared plus pi squared over 4w, and then w minus w squared. I'm not saying that this is exactly what we took. Just stay with me for 1 second. If in here I didn't have the w squared, I would have fibers, all fiber would be invariant, and I would be, if I write epsilon in here, and pi squared over 4 epsilon, and actually just put epsilon squared in here, epsilon squared in here, then you would see, the expert will recognize that I would be doing parabolic implosion. Meaning, if I take this map and I compose it and I iterate it, I stay on the fiber, And on the fiber, my fixed point, which is parabolic, becomes 2 fixed points. And depending on what I chose for epsilon, this could be 1 attracting and 1 repelling fixed point, or 2 slightly repelling fixed points, almost parabolic. And then you would have parabolic implosion. But now if I forget about this, and I take w minus w squared, well, I know what happens for wn. So when I iterate, wn is more or less 1 over n. It's tending to 0 like 1 over n. So if I take wn squared, I will have 1 over n squared. Okay? And in here, I would have pi squared over 4n squared, which is exactly what I need to have something which is mimicking parabolic implosion. It's mimicking parabolic implosion because at each step of the way, I'm changing. So whenever you iterate this map, f, you iterate, you start at a point, and then you're going to go to a different point. Yes?
In this first polynomial, it doesn't have w or w squared.
It has w. I'm taking it at the squared iterate. I'm not giving you a very exact proof.
If the square is on the index.
Yes. Yes. And I'm putting it as squared in here. Of course, you can make it maybe better. It's just that that's the way I think about it. So if you are in here, when you iterate at each step, you're not staying in the same fiber. You're getting from one fiber to the other one, to the other one, to the other one. And at each step, you're going slower. Okay? And so you can ask, okay, maybe this is the right size that I can take, the right kind of maps that I can take to have a wandering domain. To build a wandering domain that could come near by the fiber and then go out, and then come here and then go out, and etc. And so this is what has been done. So I'm sorry, I'm going to steal you 3 minutes. I mean, on my chronometer here, I have 3 minutes left. So the first result, answering to question 2, was, okay, let's talk. Unfortunately, we didn't have any C person, so we have Desjardins, others, and myself. I usually, people forget about me, but I was in the crowd. So what we proved was that, well, if you take this map, of course, this is not what we wanted. So we wanted something that is a polynomial extending to P2 and etc. So you add terms. But what we proved was that if you take ZW goes to Z minus Z squared plus pi squared over 4W plus O3. Yes. Sorry. What did I put in here? Whatever, plus O3. Okay. AZ cubed plus O3. And in here, minus W squared plus OW cubed. So this has a wandering domain for A close to 1. And I'm skippy. So essentially, question 2, the answer is yes. So it's not that we were not good enough in trying to generalize Sullivan's result to higher dimension. Is simply not true. And the proof is quite elementary, I would say. It's really essentially, in one word, as non-autonomous parabolic implosion plus a bunch of computation. And that's essentially it. So I will not enter into any details. I just want to tell you, to give credit. So, all right. So, Astorg and Botstaller. And so I think it got published this year, but I might be wrong. So they studied the dynamics of, so Z plus Z squared plus BZ cubed plus O3 w minus w squared plus OW cubed as b varies. And so they could find, if I'm not mistaken, 1 ring domains with rank 1 limit maps, among other things. Sorry? D plus d squared plus bz cubed. Yes, it's in here. Sorry, it's O3 of zw. Whatever. Yes. I mean, I don't remember. So, but anyways, this is a order 3 in z and w. Yes, it's a bw squared. Thank you. All right. Plus other things. Okay. And, well, I'm sorry, but you will not hear anything about the elliptic fibers. So, but, well, let me tell you that we studied them with Hans Petters, who's going to be in week 4 in 2017. And we have some result, but, well, let me close with this. There is some arithmetic on theta playing a role here. But I will not enter too much into details. So we could find some, well, you have to add some hypotheses, otherwise nothing is working. And I'm sorry I went over time, even if I was trying not to, so I'm going to stop here. Thank you very much.
Yeah, very interesting. Little question. Sorry, you implied it, but just to check for sure. So the wandering domain matrix that you guys constructed actually does approach the
Yes, yes. So the idea is really going nearby. It's like if it was doing parabolic implosion. So in parabolic implosion, you go out, you go back. Exactly. Yeah, sorry, I implied it, but I didn't say it. Alex, you wanted to say?
Do you know, or do you have any idea what the internal dynamics are on the wandering domain as it's wandering? Or like for transcendental mapping, that obviously very much classification.
Not much. So what happens is that what we can say is if you restrict to the n square subsequence, then you're going to converge to a point, which is an attracting point, fixed point. I'm sorry, but he's an expert, so I can say this to him. He's an attracting fixed point for the Lavor's map of f0, little f0, which is tangent to identity. So, and that's essentially how you prove that, well, first you prove that you have convergence. And so this is telling to you that you're in the Fatou set. And now you want to prove that these two wandering domain, sorry, the images are never the same. And how do you prove it? Well, if you take fn squared restricted to omega, it converges to psi 0. And fn squared plus 1 restricted to omega, it's going to converge to f0 of psi 0. But this guy is in the parabolic basin of f naught. You know that you have no other periodic point than 0 itself there. So this have to be different. So I'm doing it on, so this is simply fn squared on f of omega. So I'm telling to you that f of omega and omega are not the same, but then you do the same for any two images of omega. And that's exactly how you prove that it's not pre-periodic. But if you ask me, okay, what about the rest? No idea. But I mean, it's fair enough, I think.
If I may just add, so inside of the component, like we said, if you look at the ball, it will shrink. So the dynamics is where we experience more. Of course, going to mitigate it, it's going to get smaller, but anyhow, intrinsically, it's contracted. But you can always replace, you can also replace this contracted fixed point with a, let's say, with a rotational one, and you'll get the contraction in one direction, rotation in the other. But again, everything will converge to a pattern. So you have several different.
Any other questions? Yeah.
I don't quite know the right words for this, but can you say anything about the topological properties of these values? Comparable to significant or significant connectivity.
We did like
But I mean, actually, so there is one thing that Tom was mentioning already in the one-dimensional one. The invariant ones, where you make them bulge. You have no idea if you have something like, well, in my head they're always like this, but it turns out that depending on the compactification that you're using, you might also even have something like that. So they're all in the same guy. This could happen. So it's like then you have to really study what the situation that you're really studying. It's not so easy already to know if they're not all part of the same guy. And actually, this was a question that we had in here. Well, of course, in here, what it turns out that once you're going to one fixed point and you have to convert to a different one, you couldn't be in the same Fatou component because you have uniqueness of limits, as we teach to our students. So it's like, so you could not connect them, but you have. So I have no idea. I mean, there was some. It was on the board and I erased it. There was, I think, something about it in Roder's paper, topology of Fatou components. But I think I'm not sure. I might say something wrong, but I think he was working in the invariant or pre-periodic case. Because at that time, he didn't know that wandering ones were existing. So, but I'm not sure. I didn't check it lately, and my memory is not very good anymore.
Yeah.
Can you just tell us a little bit more about the 2 minutes about this elliptic case? So what was sort of the outcome?
The elliptic case is not a 2 minutes case, but I can try. So. Yeah, so again, if you work with regular polynomials, we're going to have bulging of the basin of infinity, and that's okay. So if I'm not, well, let me tell you, but maybe I could have freed the other, but well, sorry guys, it's useful. So essentially, okay. So you have to, you kind of have to add that theta is Bruno. So you have to be able to linearize. So if theta is a Bruno number, then you can make parabolic basin bulge. So for the Siegel disk, so Siegel disk do not always bulge. And this is due to resonances. So to give you an example, this one, even if you ask it to be Bruno, it's not going to be bulging. And then if you are in the Bruno case, plus you add some, so plus you have no Siegel disks because you cannot control Siegel disks, then you have question 2 as a no answer, which is a very easy proof. Because if you don't have Siegel disks, you're only having well, for F0, you're only having attraction or parabolic domains. And so, well, essentially what you can prove is that you can find a measure which is essentially attracting out of the Julia set. And so, well, your wandering domain should be in between, and well, it cannot. It simply is going to be smashed on the fiber again. But we cannot get rid of the Bruno condition, because if the parabolic domain, if the parabolic basin bulges, then there must be some invariant curve going around it. And that I could prove. And so, well, maybe there is a different arithmetic condition better than the Bruno one, but I have no idea what this could be. Yeah, better means that it's less strong. I don't know, weaker. But I do believe that it's a kind of, maybe one can do a little better. It's just that at some point I wanted to leave the skew product word, so I work on something else, and now I'm back to it with, but I put somebody else on it, and I think the transcendental case, yes, I wanted to finish with an open questions, and it's not so open anymore, but Tom is working on transcendental skew products, so he has very nice results, as you have seen, and he has many more that are in the process of being written, so, well, you will see more very soon. And I think it's a very rich.
Thank you very much. I think we're passing over coffee.
Yeah.